Okay, so we've been looking at this flow chart. When you're asked, what is the pH of question, which we get a lot of these in module 6 and 7. We've been looking at the strategy for answering that question by watching the flow chart and first identifying, do I have an acid or a base or a salt? And if I have an acid, is it strong or weak? If I have a base, is it strong or weak? And if it is a salt, at this point in the discussion through module 7, it will be soluble, which means it splits up into ions 100%, which means now for the two ions that are present, you have to identify, are they acidic, basic, or neutral ions? Neutral ions can be ignored. Acidic ions will be, by definition, weak acids, which means we can work a weak acid problem, as seen above in the flow chart. If the ion is a basic ion, it will, by definition, be a weak base. None of your ions will be strong acids or strong bases. It can't work that way. It doesn't work that way. So if you have a basic ion, it will be a weak base, in which case you work a weak base problem, just as seen above in the flow chart. We have, starting with the last part of Module 7 material, a new scenario when you're asked, what is the pH of? And this is when you have two things in the beaker. And your strategy is to identify the two things. Make sure I don't hit my keyboard. Are the two things, and you'll get two answers possibly, acid, base, or salt. If it is a salt, if one of the things in your beaker is a salt, split it up 100% into ions, and for each ion, identify whether it's acidic, basic, or neutral. And anything that's neutral can be ignored. If it is an acid, you identify whether it's strong or weak. You see a pattern here. If it's a base, you identify whether it's strong or weak. And so at the end of this process, I'm going to scroll up. At the end of this process, when you have two things in your beaker for Module 7, again, it's going to get a little more complicated once we get to Module 8, but for now, the two things in your beaker, once you finish identifying, will end up being an acid plus a base. If you end up with two acids or two bases, that's a little bit more complicated question, and I'm not saying I wouldn't ask that, but that's a question that gets you thinking a little bit more. But for now, most of the problems, what you have to learn in order to get your B in the class, is understanding that there is an acid and a base at the end of this identification process. That's the way it will be 99% of the time. If you're not coming up with an acid and a base, go back and look more carefully. Once you get the acid and the base identified as the two things, and again, if you've got a salt, the salt is neither acidic nor basic. It's the ions you have to look at and identify. Do I have acidic, basic, or neutral? And then ignore the neutral. All right, remember to ignore the neutral. When you finish identifying your acid and your base, the next thing you ask yourself is, are these two, is this acid-base pair, are they conjugates or not? All right, they are either conjugates or they are not conjugates. This goes back to Module 6 when we first learned about conjugate acid-base pairs. Make sure, review that if you need to in order to be able to identify whether or not this is a conjugate acid-base pair. Because how you handle the question, how you proceed with the question, what is the pH of, depends on you identifying whether or not this is a conjugate acid-base pair or not. If they are a conjugate acid-base pair, let me scroll down. You will have a weak acid and a weak base by definition, because we're ignoring anything neutral. If they are a conjugate acid-base pair, they're going to be a weak acid-base pair. They will both be weak, in which case you can work this problem as either a weak acid or a weak base. It's your choice, and you might decide which based on the availability of K values, because you may recall, in order to work a weak acid problem, you set up an equilibrium reaction for that weak acid, you look up a Ka value, you draw an ice table, and you solve for X, which is the H plus. If you choose, you can work it like a weak base problem, in which case you write the equilibrium reaction for the weak base. You look up a Kb value. You may have to calculate it. You draw an ice table. The X in the ice table will be the OH minus, where you can find the POH and therefore the pH. So when you come down to the fact that there are two things in the container and they are a conjugate acid-base pair, then that is the solution. So let's work one of those now. All right, we'll deal with the not conjugates in the next video. So we have the question, what is the pH of a solution? That contains, or that is, 0.51 molarity in sodium fluoride and 0.82 molarity in hydrofluoric acid. And by the way, this is question number 3 on your practice 14 for module 7. It had a typo in it previously, so that it was suggesting the correct answer was wrong. It was suggesting the correct answer that was wrong because I had the wrong Ka value. I have fixed it. If you have a module 7 practice 14 open from before yesterday, when you type in your answer, even if you're right, it's going to count it wrong. If you open up a fresh practice 14 quiz, it will use the updated value and it should be grading it correctly. If you're confused, post your question, your specific question with your values and your answer and what it's saying the answer is on the discussion board, and I can look it over and tell you whether or not that answer is wrong, yours is right, or no, now that's the right answer and yours is wrong. Let's look at the work. Okay, so I'm working it with these numbers. When you pull up your practice set, it will not be exactly these numbers. So what is the pH of? You'll notice that we have two things in our container. We have sodium fluoride and hydrofluoric acid. So the first thing we do is identify it. Sodium fluoride is a salt. We talked a lot in the previous video about how to recognize that that's a salt. It has two names. It is the names of the ions that make it up, therefore it's an ionic compound. It is made up of the sodium ion and the fluoride ion. So I'm splitting it up into the ions. For each ion, I'm deciding whether it's acidic, basic, or neutral. We've gone over that in a previous video just to remind you. If I have the conjugate or an ion that comes from a strong acid or a strong base, it is neutral. Sodium ion comes from sodium hydroxide, a strong base, so it's neutral. I can ignore it. Not even going to mess with it. And I have the fluoride ion whose conjugate is HF. All right. HF is a weak acid, therefore F minus is a weak base. I can't ignore it. So there's one thing in my container, the F minus ion, which is a weak base. Let's come over here to the other thing in my container, which is HF, hydrofluoric acid, which is a weak acid, which you may be going, but wait, we just talked about it. And we did, because the two things in my container are F minus and HF, and they are conjugates. So I am working this problem either as a weak acid or a weak base. It doesn't matter which way I set it up. I am putting in my initial concentration. I'm writing the equilibrium constant. I'm putting in my initial concentrations. I'm setting up an ice table. I'm solving for K, for the X, and from that I'm finding the pH. This becomes just like the previous problems that were either weak acids or weak bases, with just a little bit of nuance. So since hydrofluoric acid is a weak acid, and I have a table value for a Ka, it would be easier for me to set it up as a weak acid problem. If I had the Kb for this base, it would be easier for me to set it up as a weak base, but I don't have a Kb for F minus. I would have to calculate it. I could find it. So let's set up as a weak acid, because that's going to be easier. We can do it either way, but that will be easier. And so I'm just going to write the generic weak acid You can write it specifically. I'm going to write the generic weak acid equilibrium reaction. I'm going to go ahead and look up the Ka for hydrofluoric acid. This was what was wrong originally on the problem, but hydrofluoric acid's Ka is 6.4 times 10 to the minus 4. I've got an initial change equilibrium, and now carefully look at that problem. My initial hydrofluoric acid, that's represented by the HA, that's representing the hydrofluoric acid, is 0.82 molarity. And the initial H plus is 0, as usual. It's actually 1 times 10 to the minus 7, recall module 6, all right? But that's very, very close to 0. We just say 0. The initial A minus, that is representing that conjugate base of my acid. That's representing the F minus ion, and its initial concentration is 0.51. This looks a little different than our other ice tables. We don't have zeros in both products because we have those two things in the beaker at the same time. So there are initial amounts of two things, and they happen to be a conjugate acid-base pair, which means they show up in the same equilibrium reaction. Now I still have my minus X, and plus X. It actually wouldn't matter which side you put the minuses and the pluses on, but don't change the way you do it. We typically put the minus for the reactants, the plus for the products. 0.82 minus X, and 0.51 plus X. And now I'm going to set up my equilibrium reaction, or my equilibrium equation. Now careful, watch how I do this. This is calculated as HA to the first power times A minus to the first power divided by HA. And so that is X times 0.51 plus X divided by 0.82 minus X. Now, this is a quadratic equation, and it's a very complicated quadratic equation. You can use a quadratic equation solver if you want to. I don't suggest it. I suggest using the approximation we've been talking about. Turns out in one of these problems where we have conjugates, and I don't think I said this before, but when you have a conjugate pair in an equation, that's what we call a buffer problem. It's a buffer. If you have both a weak acid and its conjugate base, or a weak base and its conjugate acid in the same beaker, that's a buffer. And so this is a buffer problem. And it turns out with these buffer problems, X is going to be very, very small, regardless of what the Ka value is. And that's because, by definition, a buffer solution is one that resists changes in pH values. So the plus X's and minus X's are going to be very small, because that's what a buffer does, is it keeps the changes very, very small physically. So I'm going to use the assumption. We've seen that assumption before on the denominator. So let's start here. We're going to assume that 0.82 minus X is approximately equal to 0.82. That'll get rid of it there on the bottom. But we're also going to assume that 0.51 plus X is approximately equal to 0.51. This is that if I have $1 million example. If I have $1 million and I give everyone in my class $1, that's the minus X, I'm giving it away, I still essentially have $1 million. But this one works as well. If I have $1 million and everybody in the class gives me $1, that's your plus X, I still essentially have $1 million. So let's make those approximations and rewrite our equation. And the math becomes very simple. It becomes very simple algebraically to solve for X, do your cross multiplying, etc. Let me punch it in. And I get 1.029 times 10 to the minus 3. And let me double check that. All right. So with that solution, and again, I'm in the third decimal place, and both of my concentrations, the 0.51, the 0.82, are only in the second decimal place, and then my third decimal place change is a 1. That's small enough that I'm not going to have to worry about the approximation not working. If I took this x and I put it back up here, I would see that that approximation is just fine. But again, if you trust me on the buffer problem, you don't even have to mess with that. All right, so that's my x value. What was the question? Oh yeah, what is the pH of the solution? I just solved for x from the ice table, and you will notice that the x is the H plus because I set it up as a weak acid problem in this case, and therefore the pH is the negative log of that H plus, that x, and so the pH is 2.9875, and most of the time we're going to be rounding to 2 decimal places, so the pH is 2.99. And this happens to be acidic. I will point out, I talk a lot about doing a quick check to see if that pH makes sense. When you're dealing with a buffer solution, which has both a weak acid and a weak base in it, it may be acidic, it may be basic. It actually depends on what the Ka value is. But in that case, I mean, the little quick check of I'm expecting acidic is not necessarily right. Just because I wrote it as a weak acid problem, I'm not necessarily expecting an acidic pH value. So that little check doesn't work real good. But there are ways that you can check it until you get comfortable with it. And that is, let's work this problem another way. Let's go ahead and work it as if it were a weak base. So we worked it as a weak acid. I'll be posting this a PDF of this file when I post the video, so you'll see it. So let's work it as if it were a weak base. So let me bring the question back down here. All right, let's work it one more time. Oops, sorry. And see what we get. So the problem is still, what is the pH of a solution that is 0.51 molarity in sodium fluoride and 0.082 molarity in hydrofluoric acid? And let me point out as we start, we're working this a slightly different way. We should get exactly the same pH. If you have a solution that has a certain pH, that is not dependent on how you calculate it. It is that pH. So no matter which way you calculate it, you should get the same pH if you're doing the calculations correctly. And it is just as correct to work it as a weak base as it is a weak acid. So I have, again, coming down to I have a weak base and a weak acid. A minute ago, we worked it as a weak acid problem. You could alternatively work it as a weak base. And to do that, let me scroll back up. Recall that as a weak base problem, you have to write an equilibrium constant that or an equilibrium reaction starting with the weak base. You have to have a Kb value. You have to set up an ice table with x's, which is going to find your OH minus, which is going to find your POH, which means you can calculate a pH. Same procedure, but we've got Kb instead of Ka. We have a different equilibrium reaction. The ice table is going to look almost identical. And then at the end, we'll be doing POHs instead of pHs. All right. So let's write that equilibrium reaction. So I can write it as the generic. What was the generic? The generic reaction looks like this. Let me write that one first. I can always use this generic reaction. Sometimes it fits better than others. This does not a perfect fit because the base is actually F minus and its conjugate, this is the acid-base conjugate pair, its conjugate is actually HF. So technically the reaction is actually this, but I can, especially if I have a very complicated weak base, if I just want to use that weak base generic equation, the numbers work out the same as long as I remember which one is which. This represents the conjugate acid of this weak base in any generic reaction. So I can represent it either of these two ways. I'm going to have to set up a dice table. I'm also going to need a Kb. We'll look at that in just a minute. Let me do the ice table first. The F- concentration comes from the sodium fluoride, which is 0.51 molarity. Water we don't have to keep track of. The HF concentration, that weak acid, comes from the hydrofluoric acid, that's 0.82. And our hydroxide ion was starting off with 0. Again, minus X's and plus X's, it makes more sense. 0 plus X rather than 0 minus X. Technically, I could put the, I can't talking right. Technically, I could put the pluses and the minuses on either side, but it makes the math easiest if I do it that way. Okay. So there's my equilibrium values that I will be plugging into the Kb expression because this is a weak base. So what is the numerical value of my Kb? You'll notice we don't have a Kb. Our base, recall, is the fluoride ion. We don't have a Kb for it. Don't go Googling it because we need the ones from our tables, and we get it by taking 1 times 10 to the minus 14 all over the Ka for HF. We saw this in the salts video, and the Ka for HF is 6.4 times 10 to the minus 4. We saw this way of calculating a Kb or a Ka if we're dealing with a conjugate of something in our table back in the salts. You can actually go ahead and calculate it, or I often like to just continue to write it this way. I'm calculating it. You do not want to round yet. You want to keep extra significant figures. I'd keep several extra significant figures, or you can keep it in your calculator and bring it up. I'm going to store this in case I accidentally hit another button. So there's the Kb, and that will be equal to products over reactants from this equilibrium line. And so it will be 0.82 plus X times X divided by 0.51 minus X. We'll use that approximation. The plus X and minus X can be assumed to be very small compared to those original concentrations. And so we have 1.5625 times 10 to the minus 11 equals 0.82X divided by 0.51. This becomes a very simple mathematical problem. Let me punch it in. And I end up with 9.717 ... times 10 to the minus 12. Indeed, I've got a very, very small number. So the approximation is fine. Remember that my X, in this case, is the OH minus. And so the POH is the negative log of that, or 11.01, which means the pH is 14 minus that, or 2.9875, or 2.99. What do we get? 2.99. Imagine that. We end up with exactly the same pH, and we have to. We're talking about the same solution, but you can work it either from the weak acid direction or the weak base direction. Doesn't matter.